Welcome. In this video we will be sharing a proof of concept using Sumitomo Electric's Ethernet switch. First, let's briefly take a look at the history of vehicle architecture. Electrical ignition and radio were the only standard equipment in most cars in the 60s. Electronics engine control began to emerge in the 70s. Power window, power seat, and air condition had been integrated in the 80s. Safety features like ABS, airbag and heads-up display drove electrical and electronic architecture integration in the 90s. Infotainment, comfort, and convenience features continued to grow throughout the past decade. The emergence of electrification and connected vehicles in the last 5 years drove more complex electrical and electronic architecture. The complexity of EE architecture continues to grow as we move into an autonomous driving era. From 2010 to 2020, new functions such as hybrid electric vehicles, battery electric vehicles, and advanced driver assistance systems were developed. Multi-gig Ethernet was originally considered a standard for high-speed and low-latency in vehicle communications for driver assistance and automated driving. The advantages of in-vehicle multi-gigabit Ethernet is it's significantly faster than 1 gig Ether. Its high-precision images and other data communications are possible, and it has seamless in-vehicle and out-of-vehicle communication. The disadvantages are, the cost of PHY-IC chips and harnesses is high, the housing of the ECU may be changed from resin to metal, and it will be difficult to meet noise requirements because of the higher speed. Our goal is to sell automotive Ethernet products. This experiment is being conducted in order to allow the benefits and attractions of this product to be experienced in a real vehicle. Our experiment shows how ADAS system works well with Sumitomo Electric's automotive Ethernet. Moving on to the experiment vehicle's architecture. The vehicle used in the experiment is a 2019 Honda CR-V, and the base open software used is called OpenPilot by AI. These are the 6 main functions that will be conducted in the experiment. Next, we will show you how the equipment is set up inside the vehicle. This section describes the system configuration. The signals from the front camera and the driver monitoring camera, which outputs a large amount of data, are input to the PC via 2 automotive Ethernet switch ECUs. 2 lanes of 2.5 gigabits per second automotive Ethernet communication are used between the 2 automotive Ethernet switch ECUs. The PC also receives information from the vehicle's radar and controls the vehicle via CAN. All object driver recognition and vehicle controls are handled by the PC, while vehicle steering and braking are controlled via CAN. This is the equipment layout in the front cargo area. In the next scene, you will see the equipment layout for the back cargo area. We research and develop cables and connectors between 2 ESWs, automotive Ethernet switch, and ESW itself. In this experiment, we tested a long cable length of 15 meters between 2 ECUs and confirmed that the cable can be transmitted without any problem, even when the vehicle wiring is longer. Next, let's go through the experiment footage. If one of the 2.5 gigabit per second high-speed cables is removed, the OpenPilot software may be unstable on the visualization function. We decided to test on a dummy video. We have established a safe driving support experimental environment using Sumitomo Electric's automotive Ethernet switch, automotive Ethernet connectors, and cables, and confirmed that the functions of the safe driving support application work properly. The data volume of in-vehicle communication is expected to increase in the future, such as in automated driving, and automotive Ethernet is expected to be used more and more in the future. Even if one connection is lost, the software lets the autonomous ECU know that one of the redundancy cables is disconnected. Real-time and low latency are more important than large capacity transfer. Edge processing on the camera side is needed. It is important to design and build a system that does not use the CPU or GPU resources of the autonomous ECU as much as possible. Thank you for taking the time to listen to our presentation.